Hello again. This is our third lecture on matrices and solving systems of linear equations. We've seen that interplay between a system of linear equations and corresponding matrices, and then we studied matrices by themselves for a while. We talked about how you can add them, multiply them by scalars, and then the more complicated operation of matrix multiplication. In this lecture, I'd like to focus more on matrices. I'd like to develop two more very important ideas, one being the inverse of a matrix and the other being determinants of matrices. And near the end of this lecture, I'd like to also show you an application of matrix inverses to solving a linear system. And I'll ask you the following question. Do you like this new way of solving a linear system? So keep that question in the back of your mind as we progress. But first of all, what do I mean when I say inverse of a matrix? First of all, we'll be dealing with square matrices. In fact, this entire lecture will be with square matrices. Let me illustrate the idea of a matrix inverse as follows. So let A be -1, 2, -1, 1, a 2 by 2 matrix, and B another 2 by 2 matrix, 1 minus 2, 1 minus 1. I'm going to multiply A times B. Let's remind ourselves how we do that because it's a non-trivial task. So you set up the two matrices side by side, and then you multiply the first row of the left-hand matrix times the first column of the right-hand matrix, and that gives the upper left-hand entry of the product. So in this case, it's -1 times 1 plus 2 times 1, and that simplifies to 1. So the upper left-hand entry of the product is 1. Let's do the next multiplication. -1 times -2 plus 2 times -1, they cancel, giving a 0. And then the bottom left entry is also 0, and the bottom right entry, the entry in position 2, 2, is -1 times -2 plus 1 times -1, and that yields a 1. How interesting. The product of these two matrices, A, B, yielded that matrix 1, 0, 0, 1, which I called an identity matrix. And in fact, if you were to reverse A and B and write it as BA, you would get the same answer. You'd get the identity matrix 1, 0, 0, 1. Here's a rare case where the matrices actually commute. AB equals BA in this case. So what do we say in this case? Imagine with numbers, we've kind of got a product of two numbers equal to 1, like 7 times 1/7. We call those inverses of each other, don't we? Multiplicative inverses. Well, the same thing here. A and B are inverse matrices of each other. So if AB equals the identity matrix and BA equals the identity matrix, we say that B is the inverse of A, and in a similar fashion, A is the inverse of B. Some good news here. If the inverse exists, that's a big if, but if it does exist, it's unique. There's only one inverse for a given matrix if it has an inverse at all. And here's some bad news. The notation is not the greatest. It's the matrix, the inverse of A is denoted A, and you put a -1 up here. We did that earlier with inverse trig functions, didn't we? And I kind of pointed out that that's a fairly misleading notation. You might think it's 1 over A. But 1 over A makes no sense. We don't know how to divide matrices. So A inverse is that unique matrix B such that A times A inverse, or A times B, equals the identity. So here's a great question. Given a matrix, a square matrix, how do you find its inverse? What's the algorithm for finding the inverse of a matrix? How do you do it? I could do the following. I could just tell you the algorithm right now. And for many students, that's fine. They sort of tell me in class, Professor, don't confuse me with a lot of reasons. Just give me the answer. How do you do it? But let me take a moment to try to motivate this algorithm, because I think it's kind of a surprising idea. And the algorithm by itself, it's kind of no fun. It's better, I think, to see a little bit of motivation. So let me spend a couple of minutes explaining how the algorithm arises. So here's what we'll do. We'll take an example, say the matrix 1, 4, minus 1, minus 3. And I want to find its inverse. So let's call the inverse B and give its entries X, Y, Z, W. So the game is, given that matrix A, find the entries of the matrix B such that AB is the identity matrix 1, 0, 0, 1. So let's put them back to back. Here's A, 1, 4, minus 1, minus 3, times this unknown matrix, X, Y, Z, W, and let's do the matrix multiplication. Okay, what's the upper left entry? X plus 4Z. The upper right entry, Y plus 4W. The lower left, minus X minus 3Z, and minus Y minus 3W is the lower right. So I've multiplied these two together, and what do I want the answer to be? I want the answer to be the identity matrix 1, 0, 0, 1, don't I? So here I have a pair of 2 by 2 matrices, and they're equal to each other. That means the entries are equal to each other. So this gives rise to four linear equations. The first equation is equating the upper left-hand entries. X plus 4Z equals 1. And then you have Y plus 4W equals 0, minus X minus 3Z equals 0, and finally minus Y minus 3W equals 1. But notice something about these equations. In a sense, they've kind of split apart. The equations involving X and Z are over here, and then there's the equations involving Y and W. They aren't intertwined a whole lot. You've got really two systems of equations. One system involves X and Z, and the other system involves Y and W. So I have to solve two systems. Well, what else do you notice about these systems? Check out their coefficient matrices. They're the same, aren't they? Wow. The coefficient matrix is 1, 4, minus 1, minus 3, and that's the same for both systems. So if I wanted to solve each of these systems, remember, I'm trying to find X, Y, Z, W. So if I want to find X and Z, I would solve the following system. 1, 4, 1. 1 would be the right-hand side, on the constant term. And then the second row would be minus 1, minus 3, 0. I would take that matrix and do our Gaussian elimination. Solve that system. Now, if I wanted to find Y and W, I would set up another matrix corresponding to that system, and it would have 1, 4, 0, minus 1, minus 3, 1. In other words, the coefficient matrices are the same, but the right-hand sides are slightly different. One of them is 1, 0, and the other one is 0, 1. Well, and I would row reduce that matrix and get an answer. But wait, can you do even better? The row reduction for the first matrix, by row reduction, I mean those operations of multiplying one row and adding it to another row, etc. Those operations for the first matrix are precisely the same ones you'll do on the second matrix. So why not do them both at the same time? Isn't this cool? So what you do is you write a wider matrix. On the left is the common coefficient matrix, 1, 4, minus 1, minus 3. And then I like to put a vertical line here to distinguish that on the other side, I have the right-hand sides. The first system had 1, 0 as its right-hand side. The second system had 0, 1 as its right-hand side. And I'm going to glue them together. And I'm going to solve this double system. Well, how do I solve that system? Or how do I row reduce that? I apply a Gaussian elimination to that. Well, it's the same old thing, a multiple of one row added to another, blah, blah, blah. You do all that, and here's what you get when you're finished. The left-hand side is the identity matrix, 1, 0, 0, 1. And the right-hand side has been changed. It's now -3, -4, 1, 1. So magically, the row reduction algorithm has produced on one side the identity matrix and on the other side a new matrix. Let's now untangle all this. What does that system mean? Well, remember, we're solving two systems simultaneously here. The first system, if you peel off that first column, the -3, 1 part, is 1, 0, -3, 0, 1, 1. That system says that x is -3 and z is 1, because that first system involved the variables x and z. The second system says that y is -4 and w is 1. Whoa, I've solved the whole problem. I now know what the inverse matrix B is. B equals -3, -4, 1, 1. So this is the algorithm. You sort of see how it works. You take the matrix you want to invert. You put over here the identity matrix, 1, 0, 0, 1. And then you do row operations. You do Gaussian elimination, all those ugly operations, all that arithmetic, until finally on this side, which began as the matrix A, it will finish as an identity matrix, and over here will be the inverse. Not quite, of course. It may not get to the identity over here, and I'll show you an example of that in a minute. But let me first formalize this algorithm. It's a beautiful algorithm, and then we'll show an example or two. So here's the general algorithm for finding the inverse of a square matrix. Okay, the matrix is A. Write down A and adjoin to it the identity matrix. So this is now a much bigger, a rectangular matrix. It's now n rows, but 2n columns. A and the identity. Do row reduction. Do those elementary row operations that we learned about when we studied Gaussian elimination. Keep doing them until over here on the left you have the identity matrix, and on the right will appear the inverse. Whoa, there it is. There's your answer. However, it could be that you can't get the identity over here, and then you'll conclude that the matrix does not have an inverse. All right, and I've kind of written this in a formalized pattern. A vertical line I, row reduction to I vertical line A inverse. Let me show you an example. This example is a 3 by 3 matrix. 1, -1, 0, 1, 0, -1, 6, -2, -3. How could you find its inverse if it has one? Well, the algorithm says adjoin to it on the right the identity matrix, and now it would be the 3 by 3 matrix. Do row operation. Now, don't make me do it in front of you. This would take by hand 20 minutes. But a calculator can do it instantaneously. And you end up with, on one side, the identity matrix, and over there on the other side, magically, the inverse has appeared. And there you see it. The inverse turns out to be -2, -3, 1, -3, -3, 1, -2, -4, 1. I invite you to check that A times that inverse indeed yields the identity. Here's another example, almost the same, well, another 3 by 3 example. 1, 2, 3, 4, 5, 6, 7, 8, 9, kind of a cute little matrix. What's its inverse, if it has one? Well, you do the same algorithm, plop the matrix here, the identity here, do those row operations, but look what happens here. When you're doing the row operations, you end up with a row of zeros on the left-hand side. And that indicates that you can't find the inverse because it doesn't have one. And when a matrix doesn't have an inverse, we use the word singular to describe it. It's sort of a bad matrix. It doesn't have an inverse. It's called singular in the literature. Now, if you're dealing with big matrices, you have to use this algorithm. With 2 by 2 matrices, it's pretty simple to find the inverse. There's a little formula that I'll show you, and you can verify that it works. So given a 2 by 2 matrix ABCD, where ABCD are random numbers, its inverse is the following. Well, the matrix is D minus B minus CA times a certain scalar, a certain constant. And that constant is 1 over AD minus BC. 1 over the product AD minus BC. That product, by the way, is called the determinant of the 2 by 2 matrix, and a topic we'll come to in a moment. Let's do a quickie example. Let's let A be 3 minus 1 minus 2, 2. What's its inverse? Well, you could use that previous algorithm if you want and row reduce things, or we could use our new formula. Here's what it says. The coefficient in the front is 1 over AD 3 times 2 minus BC minus 1 times minus 2. And then there's a new matrix here. How does that new matrix work? Well, the diagonal AD gets flipped to DA, so it's now, instead of 3, 2 down the diagonal, it's 2, 3. And then the other entries have minus signs in front of them. So instead of minus 1, minus 2, it becomes 1, 2. And simplify. That quotient there turns out to be 1/4 times that matrix, 2, 1, 2, 3. And if you want, you could bring the 1/4 inside, scalar multiplication. The inverse turns out to be the 2 by 2 matrix, 1/2, 1/4, 1/2, 3/4. And I invite you to verify that indeed that is the inverse of A. So you be the teacher for a moment. Student comes running up to you. You've just explained this fancy new formula. Student comes running up and goes, "Professor, it doesn't work. I don't like your new formula. It doesn't work on this matrix." "Look, teacher, the matrix 1, 2, 3, 6, if I try to use your formula, when I do AD minus BC, remember that formula involved 1 over AD minus BC. When I plug those in, I get 1 times 6 minus 2 times 3. I get 0. And you told me, teacher, that I can't divide by 0 in mathematics." What's going on here? How do you answer this student who claims this formula is not working because of division by 0? Oh yeah, that matrix A doesn't have an inverse. It's what we called a singular matrix. And if you try to use the other algorithm on that matrix, you'll discover you'll get a row of zeros, and you cannot find its inverse because it doesn't have one. Okay, remember this problem we did last lecture where we fit a parabola through 3 data points. Let me show you how this inverse matrix can be used to solve this problem a slightly different way. And then I'll ask you a question I talked about at the very beginning of this lecture. Do you like this new method? So here's the setup again. 3 points, 2, 0, 3, minus 1, 4, 0. 3 points in the plane. I want a parabola that passes through all 3 of them. Let's call the parabola ax squared plus bx plus c, trying to find A, B, and C. Okay, this gives rise to 3 equations, 3 unknowns, just like we did it last time. And remember that coefficient matrix was 4, 2, 1, 9, 3, 1, 16, 4, 1. The unknowns we wrote as a column matrix, A, B, C, and then the right-hand side was 0, minus 1, 0. And we looked at that, and we solved it, say, with Gaussian elimination. This time I'm going to do it slightly differently. Write that equation in the compact form, AX equals B. And think about it now. Gee, if that were an algebraic equation, if I forget about matrices and I go back to algebra, and if I have an equation AX equals B, where A and B are just numbers, what's X? Oh, it's B over A. You would multiply by A inverse, wouldn't you, to solve that? Well, we're going to do the same thing with matrices. So to solve the equation AX equals B, multiply on the left both sides by the inverse of A. And A inverse times A will cancel. They'll give the identity matrix. And then the right-hand side is A inverse B. And so we have the equation, the identity matrix times X, which of course is just X, equals A inverse B. Theoretically, this looks really nice. You have this linear system, and it could be any old system with a square coefficient matrix. You find the inverse of that coefficient matrix, and the answer is a simple equation, A inverse B. That looks really simple, doesn't it? In this case, I won't bore you with finding that inverse, but it turns out to be a 3 by 3 matrix. A does have an inverse. And if you multiply that inverse times B, indeed you get the answer we had last lecture, 1 minus 6, 8. What do you think of this method? Is this a good method? Remember how it goes. To solve a system AX equals B, invert A, find the inverse of A, and then your answer is nothing more than X equals A inverse B, a simple multiplication. What do you think about it? Is this a better method than Gaussian elimination, that process we learned about a few lectures ago? Well, I hope you see that, this is really not a very good method, because to use it, you have to find A inverse, don't you? And that takes a lot of work. A inverse requires all those row reduction, all those steps of Gaussian elimination. So in theory, it looks like a nice method. Whoa, very clean. X equals bleh. There's the answer. In practice, this is not really a good method and is never really used in real life. In real life, in real applications, when you're confronted with a linear system, everybody, I shouldn't say everybody, but most people will solve that linear system with Gaussian elimination. Now, there's some other techniques for solving system, the Gauss-Jordan method. There are certain what are called iterative methods, but the technique we've learned in these lectures of row reducing, that is the mainstream method for most linear systems. Okay, let's move to determinants. And we saw what they were briefly when we did that little formula for A inverse for 2 by 2 matrices. So let me define what a determinant is. Given a 2 by 2 matrix, I'll start with 2 by 2s. Given a 2 by 2 matrix ABCD, we define its determinant to be AD minus BC. It's that cross-diagonal multiplication. As usual in math, sorry about this, there are lots of notations for determinant. The one I prefer is DET, determinant of A. But some books put vertical lines around A. That really confuses me. That's like absolute value of A. And then others will put the vertical lines around the entire matrix A, B, C, D. That also sometimes confuses me because I'm not sure if I'm looking at the matrix or its determinant. So let's try to use just determinant of A if we remember, but we should be aware of all those notations. Okay, some quick examples. A is 2 minus 3, 1, 2. What's its determinant? Pretty easy. It's 2 times 2 minus 3 times 1. 4 plus 3 is 7. How about 2, 1, 4, 2? Piece of cake. 2 times 2 minus 1 times 4. That determinant is 0. Is that matrix we just looked at invertible? Does it have an inverse? It doesn't. Remember, if the determinant is 0, you are singular. You do not have an inverse. Okay. Now that was the definition of determinants for baby matrices, 2 by 2 matrices. What about a 3 by 3, or a 4 by 4, or a 10 by 10, or 1,000 by 1,000? Well, trust me, it's a non-trivial computation. Again, fortunately, these are built into calculators, so nowadays we don't really have to compute determinants by hand very much. But I thought I'd, what's the word? I don't want to say torture you here, but I thought I would show you a pretty complex calculation of a 3x3 determinant, just to give you a taste of how tough it can be. Let's find the determinant of a 3x3 matrix. And I'm just going to sort of show you the algorithm, but I'm not going to explain where it comes from. Here's the matrix: 1, 4, minus 2, 3, 2, 0, minus 1, 4, 3. What's its determinant? Now, the good news is you could plug this into your calculator or your computer, and it will spit out the answer and you don't have to know how it did it. But I'm going to show you sort of the fundamental way of doing it, and then I'll talk about it. So this is called expansion across the first row. The determinant of that matrix, here's how you do it. Look at the first row of the matrix. The first entry is 1. And 1 is then multiplied by the determinant of the matrix you obtain by deleting the row in the column where 1 lives. So that submatrix, that smaller 2x2 matrix, is 2, 0, 4, 3. You see how I got that little bitty 2x2 matrix? 1's in the upper left. I removed its row and column, and I'm left with a 2x2 matrix. Then you step over to the 4, and you multiply it by its 2x2 matrix you obtain by deleting the row in the column where 4 lives. So that leaves 3, 0, minus 1, 3. But there's a further kicker here. This is why this is an unpleasant task. In front of the 4, you have to put a minus sign. There's kind of a checkerboard pattern here where the signs go plus, minus, plus. And if it were a bigger matrix, it'd go plus, minus, plus, minus. Okay. What about the third piece? Minus 2 times the determinant of its submatrix, 3, 2, minus 1, 4. Then you find the determinants of those little 2x2 guys. Well, those are pretty easy. 2x2s are easy. So it's 1 times 6 minus 0, minus 4 times 9 minus 0, and then minus 2 times 12 plus 2. 3 times 4 plus 2 times 1. And then simplify that, you finally get minus 58. Ouch. Complicated algorithm. Multiply a number by the submatrix you obtain by deleting the row in the column, and remember that plus minus checkerboard pattern. But you see what happens here? This 3x3 matrix gave rise to 3 2x2s. So what if I had given you a 4x4 matrix? Well, you would expand across the first row, and that would give rise to 4 3x3 matrices. And then you would do each of those like I just illustrated. Ouch! What if I had given you a 5x5 matrix? You're starting to get a headache probably. You'd have a 5x5, you expand across the first row, remember the checkerboard, plus, minus, plus, minus, plus, and each of those will give rise to a 4x4. So you'll have 5 4x4s, each of which gives rise to those 3x3s. It's a terrible way to actually calculate a large determinant. And in fact, fortunately, in real life, there are completely different methods for calculating determinants that are much, much faster. And in fact, they involve those same row operations that we studied with Gaussian elimination. And again, the good news is these are built into calculators and computers, and that's why I'm not going to spend too much time on them. In today's world, we tend not to ask students to calculate determinants very much because it's really not necessary anymore. All right. We've really, I think, had a good look at linear systems of equations, matrices, and their interaction. And then we've talked about matrices as a standalone idea. You can add them, you can multiply them together, you can find their inverses if they're invertible, you can find their determinants. There's all kinds of things you can do with matrices. So what we're going to do in our fourth lecture and final lecture on this topic, we're going to look at some real-life problems. We're going to apply our skills of linear systems and matrices to show some applications of these ideas. So I look forward next time to seeing you when we talk about applications of linear systems and matrices. Thanks.